All right, on 177, section 3.6, chain rule, we're finally going to get a way that we can find the derivative of a quantity. Up until this point, if we were asked to find something like the derivative of the square root of x squared plus 1, I don't have a way of doing that with a shortcut. I would have to go back to the definition of derivative. Because even though I have my power rule that says, okay, I could rewrite that as x squared plus 1 to the 1/2, and I have a power rule that lets me deal with quantities raised to an x, or with variables raised to an exponent, I do not have a rule for quantities raised to an exponent. I know what to do with x to the 1/2, but not with a quantity raised to the 1/2. And that's why I need chain rule. In essence, what we're looking at right here with capital F of x, that's a composition of two functions. It's as if we let u be equal to x squared plus 1 if we were to decompose this function. Remember when we did compositions of functions, they also had us decompose them to break them back apart. So it would be as if I said, okay, let's let u be equal to x squared plus 1. And then the other function would be the square root of u. So that if I did that composition, if I put this function back into this one, that's where I'm getting that square root of x squared plus 1. So I have one function plugged into another. So when I have a composition of functions like that, I'm going to need to use my chain rule in order to find the derivative. And so here's what they give me for the definition of my chain rule. If your function is a composition of f and g, and you might prefer to write it this way, that's perfectly fine, then to find the derivative, you are going to simply take the derivative of the outside function times the derivative of the inside function. More specifically, when you go to find the derivative of that composition, you're going to take the derivative of the outside function f of x, and it's going to have g of x sitting inside of it. And then you're going to multiply that times the derivative of g of x. Now, if we think of this, this is kind of like our Newton notation, and this is kind of like our Leibniz notation. I really love the Leibniz notation for this, because if I am trying to find the derivative of y and it's in terms of x, I don't know how to take the derivative of that composition. But if I will decompose that function, and I'll break it back apart into the two pieces that we mentioned before, I do know how to take the derivative of each of those functions. And so here's how I could think of, using Leibniz notation, here's how I could think of chain rule. I want to take the derivative of y, and you'll notice that when I decompose this function, y was in terms of u. So I want to take the derivative of y in terms of u, and then that would be the derivative of my outside function, and then I want to multiply that by the derivative of my inside function, and that inside function was u, and you'll notice that u is in terms of x. So I can say the derivative of the inside function in terms of x. And it's almost as if, you'll notice like the du here would cancel with the du here and take you back to that dy over dx. So I'm not changing anything. So if I were to do that, I could say, okay, y is the square root of u, that's u to the 1/2. The derivative of u to the 1/2 would be 1/2 u to the negative 1/2. And the derivative of x squared plus 1 would be 2x. That's not anything new to us. So according to Leibniz notation, if I wanted to do chain rule, I would take the derivative of y in terms of u, so what I found right here, times the derivative of u in terms of x, what I found right here. The derivative of the outside times the derivative of the inside. Now, the derivative of the outside function was in terms of u. When I started with this problem, everything was in terms of x, right? So I need to back substitute. I need to put whatever u was equal to back into that problem. So if u was equal to x squared plus 1, then I'm going to put x squared plus 1 back in the place of u. And then I just want to do obvious simplifications, not anything crazy. But of course 1/2 times 2 would simplify down to be 1. You could leave this x squared plus 1 to the negative 1/2 in the numerator, or you could put it in the denominator and get rid of your negative exponent. You also could put it under the square root to get rid of the 1/2 if you wanted to. So several different ways that we could write that. So when I do a composition of two functions, one inside of another, the problem is typically I have a quantity that I don't know how to deal with. If I think of that as two separate functions, like a decomposition, I can literally go through and I can take the derivative of y in terms of x by doing the derivative of the outside function y in terms of u times the derivative of the inside function u in terms of x. And you can see how we got that here. Now, I'm going to do chain rule a bazillion times between now and the end of my calculus career. So once we get an understanding of what the chain rule is and how it works and the formal definition of it, as we've just gone through here, we looked at both of the definitions that they gave us on page 177, both the Newton's and the Leibniz notation. I really want to get to, please give me the most practical way that I can do this that's going to be the most efficient way to do this for the rest of my calculus career. So here's what I can do. If I'm trying to find the derivative of f of x, and we had the square root of x squared plus 1, so we rewrote that as x squared plus 1 to the 1/2. The problem is the quantity, that x squared plus 1. I know how to take x to the 1/2. I know how to do the derivative of that, but I don't know how to raise that quantity to the 1/2. That's the problem. Here's how I can think of this in a practical, efficient way. I can say, let's take the derivative of the outside function. So I'm going to ignore whatever is inside my parentheses here because my outside function is this 1/2. So I'm just going to refer to this as something. All right, I have something raised to the 1/2. I don't care what that something is. It can be x squared plus 1. It could be cosine squared. It could be smiley face. It doesn't matter. I have something raised to the 1/2. Anytime you have something raised to the 1/2, when you take the derivative of that, it's 1/2 whatever that something is to the negative 1/2, right? So it doesn't matter whatever it is that you're taking to the 1/2, when you take the derivative of that, it's 1/2 that thing to the negative 1/2, right? So that's going to be the derivative of my outside function. 1/2 of something to the negative 1/2. It does not matter what that something was. It doesn't matter what that quantity was. I'm literally just going to bring it along for the ride. I'm only concerned with the outside function. So I had something raised to the 1/2, a quantity raised to the 1/2. So the derivative of the outside function would be 1/2 that quantity to the negative 1/2. I don't touch that quantity at all. I just bring it along for the ride. Okay? Then I want to multiply by the derivative of the inside function. That's when I can address my quantity. I can go back and say, okay, the inside function was x squared plus 1, so the derivative of that would be 2x. And if you'll notice, in one step, we are all the way here. I did not have to write this as a decomposition of functions. I did not have to use u substitution. I did not have to take two separate derivatives and multiply them and back substitute. And so we're trying to, now that we understand the definition, we're trying to get a practical way of doing this. Okay? And so then we could simplify. This is one of those things that the more examples that you see, the more concrete it will get, and it just takes repetition. So let's just keep working some examples, okay? Look at the next one. For the next one, I have the derivative of sine x squared. If that was just derivative of sine x, I'd be good, right? Because I know how to do that. But I don't know the derivative of the sine of a quantity. It's that quantity that's causing me a problem. That's a composition where I took x squared and inserted it into sine x. So it's a composition of two functions. It's a quantity that I don't know how to deal with. So let's start with the derivative of the outside function. It does not matter what is in here. Again, if that was sine of smiley face, I could still take the derivative of it because the derivative of sine anything is cosine of that thing. Right, so that's my outside function. The derivative of sine is cosine, and I'm just going to bring along that quantity for the ride. Not going to touch it at all. Just bring it along. Derivative of the outside function. Now I want to take the derivative of the inside function. The inside function is that quantity. So the derivative of x squared is 2x. And I'm done. Maybe put your 2x out in front because we typically write it that way, but that's all the simplification that I need to do. All right, look at another one. X to the third minus 1 to the 100th. Until this time, if I saw that problem on a test, I'd be like, I don't care how many points it's worth, just go ahead and count it wrong, right? I mean, there's no way. I'm not using Pascal's triangle or some kind of craziness to expand that out to the 100th power and then take the derivative of all 8 million of those terms. No way. So I can go through and I can say, let's take the derivative of the outside function. It doesn't matter what's in here. I have something to the 100th. So what's the derivative of anything to the 100th? Yeah, 100, that thing to the 99th. Right, so 100, the quantity, to the 99th. So that's the derivative of my outside function. Now I want the derivative of my inside function. So the derivative of x cubed minus 1 would be 3x squared. And I'm done. I just need to simplify. So I could take the 100 times the 3 and get 300x squared. And of course I'm not multiplying out my power to the 99th. All right, look at another one of those. Example 4, I've got 1 over the cube root of x squared plus x plus 1. The first thing I want to do, I really don't want to use quotient rule, right? So if there's a way to rewrite this to make it more simplified before I start taking the derivative, we've learned to do that. So I want to rewrite this as an exponent so that I could use power rule, okay? So I have a quantity to the negative 1/3. If you have anything to the negative 1/3, what do you do with that? Yeah, so I'd have negative 1/3 times that quantity to the what? So no matter what that was in the parentheses, it's irrelevant. If I'm taking the derivative of my outside function, something to the negative 1/3, it's going to be negative 1/3 times that something to the negative 4/3. Negative 1/3 times the quantity to the negative 4/3. That's the derivative of my outside function. Now I need the derivative of my inside function. So what's the derivative of the inside function? 2x plus 1. So I could distribute this negative 1/3 to the 2x plus 1. So that would give me negative 2/3 x minus 1/3. And you could leave this quadratic to the negative 4/3, or you could move it down into the denominator to get rid of the negative, or you could put it under a cube root to get rid of the exponent, however you want to write it. I'm going to leave mine this way, but there are, of course, several different ways that we could write this. Okay? So we want to tonight just stop here and have some time practicing with the basic chain rule. And then tomorrow we'll come back and we'll do some more elaborate examples once we've had a chance to practice this a little bit and kind of nail it down a little bit, make it a little more concrete for ourselves. Okay?